In this video, we are going to look at Newton's laws. Hi, this is Sean Huang from the physics department. Newton's first law says that an object continues in a state of rest or in a state of motion at a constant velocity, unless compelled to change that state by a net force. In short, in the absence of a force, an object is either at rest or moving at a constant velocity, the direction of which will not change. Newton's second law says that F equals to ma. There's a summation sign in the front, which can be omitted if F is understood to be a sum. Incidentally, sum, net, and total, they all mean the same thing. Notice that the acceleration will always be in the same direction as the net force. For Newton's third law, we are going to go with the statement just below the box. For every action, there's an equal but opposite reaction. While we're at it, let's also look at Newton's law of universal gravitation, which says that between any pair of masses, there's an attractive force, the magnitude of which is given by equation 4.3. The three Newton's laws should be understood as one body. We will start with the term action. Action is actually not a force per se. Rather, it is the product of mass in acceleration. When an object M exhibits an acceleration A, based on Newton's second law, we must conclude that it is being acted upon by a force. If F is 0, since the mass M cannot be 0, the acceleration A must be 0, which means there's no change in velocity, which in turn means the velocity is a constant. This constant can be 0, which means the object is at rest, and we are back to Newton's first law. If an object is being acted upon, and therefore having a non-zero acceleration, then Newton's second law says that there must be a force. But Newton's second law does not say where the force will come from. It takes Newton's third law to declare that this force cannot come from the object itself. It has to come from somewhere else. To see this, let's again look at Newton's third law, which says that actions occur in pairs, and therefore cannot exist in isolation. If there's only one object in the entire universe, it would not be acted upon, because if it were, it would have to act back. But being alone in the universe, there's nothing it could act back on. As an example, let's look at an apple falling from the apple tree. From chapter 2, we know that it will be in free fall with an acceleration of 9.8. In other words, the product ma is non-zero, and the apple is being acted upon. Newton's second law says that there must be a force behind this action, and Newton's third law says that this force cannot come from the apple itself. And it took Newton to realize that this force came from the Earth. According to Newton's law of universal gravitation, this force is equal to G, followed by m1 and m2, and divided by r squared. If we take m1 to be the apple, m2 the Earth, and r the distance in between, which is taken to be the radius of the Earth, then we can see that the bunch of constants in the parentheses will compute to 9.8. In other words, the force, which in this case is a gravitational force, is equal to the action. Lastly, since in the universe there are no rings for the objects, if m2 can act on m1, then m1 can act back on m2 in revenge, so to speak. So, for every action, there's an equal and opposite reaction, and that is the third law. In summary, since Newton's laws should be understood as one body, the equation F equals to ma actually embodies the three laws. The first law is a special case of the second law. The second law is the equation itself. And the third law says F cannot come from the object in, it must come from somewhere else. One last note, because the value 9.8 is unique and uniquely important, it gets the designation G.